Hello friend, welcome to the course Multivariate Procedure with R. You can recall that in the last lecture we had understood an overview of the regression analysis, and I had given you some basic fundamentals like when a model is called as a linear model, what are the different steps in regression analysis, and I have tried my best to give you an overview that how this analysis is conducted. And as I mentioned that there are many more steps which we will not be covering in this topic, but surely I would recommend you that you try to follow a book also, but certainly I can promise you that I will try to cover those many topics in this lecture that will help you in understanding all the lectures in the regression analysis which have not been covered in the book, right? So now, what are we going to do in this lecture? You know, whenever we are trying to think about a statistical modeling, what are we trying to do and what do we expect? Basically, if you try to do the computation manually, it will take a very long time. So definitely we are going to depend on the software. But many times what people do that they will simply try to feed the data, they will try to input the data and they will put some click, 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 and then they will say, okay, the regression analysis has been done. But when they try to look at the software, they cannot understand what are these values trying to say. And as we have understood now that software is our obedient servant. It will do exactly what we have programmed or what we have asked. But how to interpret it, how to understand it, this is our job. So now in this lecture, I am going to cover the topics which are produced in the output of a software when we try to do the regression analysis or multiple linear regression analysis. Once you understand that how these values have been obtained and what they are trying to interpret, then it will be easier for you to understand the outcome of the software. And based on that, you can take a wise decision about the statistical modeling. Well, I'm not going to give you here the mathematical proof of all those results, but surely I will give you the mathematical expressions which are obtained after a due mathematical and statistical analysis. So let us try to begin this lecture and we try to understand different types of basic definitions and basic concepts in the multiple linear regression analysis. Okay, so now in this lecture, we are going to talk about the estimation of parameters. Well, this I will try to show you that whenever you are talking about the statistical modeling, that is equivalent to saying that you want to estimate the parameters. So now how to get it done and what are the different other aspects related to the estimation of parameters, we are going to now understand. So suppose an experiment is conducted a small a number of times and the data is obtained here like this, right? Suppose we have here k independent variable or k explanatory variable x1, x2, xk, which are given certain values. Suppose x1 is given the value x11, x2 is given the value x12, xk is given the value x1k, and based on that we try to observe the value of the response variable, which in this case is indicated by here y1. So y1 is corresponding to the observation number 1, which is obtained by giving suitable inputs to the variable x1, x2, xk. And now this experiment is repeated and we try to take another set of values of independent variables on x1, x2, xk as x21, x22, x2k, and we try to obtain the value of here second observation on the y or second observation on the response, which is indicated by here say observation number 2. And similarly we try to repeat this experiment small a number of time and we choose say different values of explanatory variables xn1, xn2, xnk, and based on that we try to observe the value of yn, which is our nth observation. So now you can assume a linear relationship between this y and x1, x2, xk. And we had discussed in the last lecture that how are we going to represent a linear relationship between y and x1, x2, xk using the parameters beta 1, beta 2, beta k, which are called as regression coefficient, and introducing an element of random error, that is epsilon. So now the general relationship between y and x1, x2, xk is now written here as say y is equal to beta 1 x1 plus beta 2 x2 plus beta k xk plus epsilon. Right. So now if you try to understand, I will try to explain you the same thing through a same example that we introduced in the last lecture. In the last lecture, we had considered the marks of 20 students, and they were indicated by y, and out of 250 marks. And then these marks were supposed to be dependent on x1, x2, x3, where x1 is indicating the number of hours of study in a week, number of assignments submitted in a month, and number of hours of play in a week. And this is how we had got this data. Right. So you can see here, these are the y1, y2, yn. This is n equal to here 20. So this is my here y1, this is my here y2, this is y3 up to here. This is my here y20. This is my here x11, this is my here x12, and x15 is my here x13. Right. Similarly, if you try to see here, this is my here x21, this is here x22, and up to here x23, and so on. Right. So this is how I am going to introduce this thing. So I'm trying to say that now I have conducted the experiment 20 times, where I have three explanatory variables x1, x2, and x3, and then I have given different sets of values to this x1, x2, and x3. For example, if I give choose the value x1 equal to 34, x2 equal to 3, and x3 equal to 15, then I get here the first observation y1 as 180. Similarly, and I try to take here the third set of values here, x1 equal to 15, x2 equal to 3, and x3 equal to 11, then I get the third observation y3, which is 118. So this is how I have conducted this experiment, right? Now, I assume that each set of this observation is also going to follow the same multiple linear regression model. For example, if you try to see here, this is our assumed relationship between y and x1, x2, xk. So I believe that each set of observation, like as here between y and x1, x2, xk, they are going to follow the same relationship. Right. So if I try to say here in very simple words, suppose if I take here this x11, x12, x1k, and here y1, so they are going to follow the, or they are going to satisfy this relationship y equal to beta 1 x1 plus beta 2 x2 plus beta k xk. So these relationships I can write for small n number of observation here like this. For example, for the observation 1, we have here y1 is equal to beta 11 x11 plus beta 12 x12 up to here beta k x1k plus epsilon 1. And similarly, for the nth observation, we have here yn is equal to beta 1 xn1 plus beta 2 xn2 up to beta k xnk. This is my here observation number. Now, these n equations can be written in a matrix format. I believe that this much you have done in your course in mathematics, that how you can write the linear equations in the form of a vectors and matrices. For example, if I try to give you here a very simple example, suppose if I write down here y is equal to 2x1 plus 3x2, and if I try to write down here y is equal to 4x1 plus 5x2, right? So I can write down there as say y1, y2 is equal to 2, 3, 4, 5, and here x1 and x2, like this, right? And we generally, you have seen in mathematics, we try to denote it by a very popular symbol y equal to ax. right, where y is this vector of y1 y2, x is a vector of x1 x2, and a is a matrix of 2 by 2 matrix of the element 2 3 4 5. Similarly, I am trying to write down here these y1 y2 yn as here in the form of a n cross 1 vector, which is indicated by here y, right. Similarly, I try to combine here all these x1, x2, x1k, x21, x22, x2k up to here, xn1, xn2, xnk in this matrix here, like this, right. So this is here a n cross k matrix, which is indicated by here capital X. And then I try to combine all these beta 1, beta 2, beta k like this here in the form of here a vector, right, k cross 1 vector, which is here like this, and this is indicated by here beta. And all these epsilon 1, epsilon 2, epsilon n, they can be combined in a n cross 1 vector like here this, which is indicated by here epsilon, right. So you can see here all these small n number of equations which are indicating the n tuples of observations can be represented in the form of a equation y equal to x beta plus epsilon, right. And if you try to understand from the earlier example what are we trying to do here, then for example, for the first set of observation here like this is x11, x12 and here x13, and this is y here y1 equal to 180. So I am trying to write down here y1 is equal to 180 is following regression equation model beta 0 plus this 34 times beta 1, then this 3 times beta 2, and then this 15 times beta 3 plus epsilon 1. Yes, I have introduced here the concept of beta 0 because I will try to explain you in the next slide, right. And similarly for the second set of observation, I am saying that this is my second set of observation, and I am saying that now this y is equal to 116 is equal to 12 into beta 1, 1 plus 1 into beta 2 plus 13 into beta 3 plus epsilon 2, and beta 0 here is the intercept term. And similarly, if you try to go for the last observation, say y20, so y20 is equal to 197 is equal to beta 0 plus 34 beta 1 plus 1 into beta 2 plus 19 into beta 3 and plus epsilon 20. So now you can see here y has been expressed as a vector of 20 by 1 order, and x has been expressed as a 20 by 3 matrix of observations on the explanatory variables x1, x2, x3, where each of the explanatory variable has 20 observations, right. So now if you try to understand this model on which we are going to now work, this is here y equal to x beta plus epsilon, where y is a n cross 1 vector of the observation on the response variable y1, y2, yn, and x here is a matrix of order n by k, where n observations on each of the k explanatory variables are obtained, and beta is a k cross 1 vector of the regression coefficient beta 1, beta 2, beta k, and epsilon is a n cross 1 vector of the random error components epsilon 1, epsilon 2, epsilon n. Right. Now, in many situations, you would like to have an intercept term in the model, right? What do you mean by intercept term? For example, if I try to write down here the model, say 1 beta 0 plus beta 1 x plus epsilon, and say another model is my here y star is equal to beta 1 x star plus epsilon star, right? So, what is the difference between the two models here? Let me try to write down here beta 1 star. So, if I assume that expected value of epsilon or expected value of epsilon star is 0, then if I try to take expected value of y, this is equal to beta 0 plus beta 1 x from here. And if you try to see when x is equal to 0, then average value of y is equal to beta 0, right? But if I try to take here the second model, then expected value of y star is equal to beta 1 star x star plus expected value of epsilon star, which is equal to 0. So if I take here x star is equal to 0, then average value of y star is also coming out to be 0. So now there are two types of situations in real life. Sometimes when you put all the values of independent variables to be 0, even then there will be some outcome for y. For example, if you try to take the example of a crop, in case if you don't put any additional fertilizer, additional irrigation, etc. in the field, and if you just throw some seeds in the field, then after some time you will get some crop in general conditions, right? So in that case, what will happen, that if all the independent variables takes value 0, that means no additional fertilizer, no additional irrigation, etc., then even then you are getting some output. So in such a cases, I would like to have a model which has got intercept term. But on the other hand, if you try to measure the light of a bulb and the input current, so in case if you make the input current to be equal to 0, that means you simply switch off the light, then the current becomes 0 and the light also becomes 0. So in such a cases, when independent variable current takes value 0, then the outcome y takes value 0. So in such a condition, I would like to have a model which is not having the intercept term. So intercept term is like this one, y star is equal to beta 1 star x star plus epsilon, like this one, right? So the role of intercept term comes in those situations where the output is not going to be 0 when the values of all the input variables are 0, right? Or in a way, in case if you take all the input variables to be equal to 0, then if your output becomes 0, then you try to consider a model without intercept term. But in case if the output does not become 0, then you try to consider a model with intercept term, right? So now if you understand it mathematically, your this X matrix here is like this, where your first column is x11, x21, xn1. Suppose if I try to make this element in the first column to be equal to 1, like as here, right? And then remaining is your here the values of independent variables. So obviously, when I am trying to take the first column to be 1, and if I want to uh, retain only the k numbers of explanatory variables in the model, then instead of x1, x2, xk, I will be having x1, x2 here, xk minus 1, right? But anyway, the moral of the story is that if you want to have an intercept term in the model, so just try to consider the first column in the X matrix to be 1, 1, 1, 1. That's all, right? So but in this case, you have to be careful that there will be only k minus 1 explanatory variables in the model. This I am emphasizing because later on you will see when we are trying to conduct the test of hypothesis, then the degrees of freedom will be depending on the number of explanatory variables in the model, and in that test situation, you will have to understand whether there are say, k variables in the explanatory model or k minus 1 explanatory variables in the model. So surely if you try to say see here, the first independent variable here, let me call it here as x star, this is taking here value 1, 1, 1, 1, 1, but it is also a explanatory variable, right? So this is what I meant when I try to take a model with or without intercept term. Okay, some basic assumptions are needed in the regression modeling in order to estimate the parameters and in order to explore the further statistical properties of the estimators of the regression coefficient, right? And they are helpful when we try to draw the statistical inference. So in the model y equal to x beta plus epsilon, we try to make here certain assumptions. So first assumption here is expected value of epsilon is equal to 0. That means on an average, the random errors are going to be 0. So whenever we are trying to observe some data, then some of the data may have error in the positive direction, some of the data may have error in the negative direction. So if you try to take the average of all the errors, that will come out to be very close to 0, or say exactly 0 ideally. Then we try to assume that the covariance matrix of the random error components is a diagonal matrix and whose all the elements are sigma square. That means I am trying to say here epsilon 1, epsilon 2, epsilon n, they are IID, identically and independently distributed. Independently and identically distributed. This means what? This means the one assumption I am trying to make, that each of this epsilon I has got variance sigma square for I goes from 1 to n, and covariance between epsilon I and epsilon j is equal to 0 for all I not equal to j. I goes from 1 to n and j goes from 1 to n. Right. So this is what I mean. Right. So if you try to see here, this is the covariance matrix like sigma square, sigma square, sigma square, and all other elements on the off and off diagonal matrix are 0. Third assumption I make here is that the rank of the X matrices is equal to K. That is, X is a full column rank matrix. What does this mean? Actually, this is trying to indicate that here all x1, x2, xk are linearly independent, or in some way I am trying to say there does not exist any exact relationship among x1, x2, xk. Right, and this condition will also be needed when we will try to make an inverse of the matrix X transpose X. Right. So, because in that case it has to be a non-singular matrix. So, if X is a full column rank matrix, then this X transpose X will be a non-singular matrix. But anyway, that I will show you later on. The fourth assumption here is that X is a non-stochastic matrix. That means X is non-random. So, well, in many cases X can also be random, but anyway for our analysis we are assuming it to be non-random, because it will help us when we try to take different type of expectations. Then and the statistical calculation will become simpler and easy to understand. And the meaning of this statement is that if you try to conduct the experiment again, possibly you will get the similar value. The fifth assumption is that epsilons are following a multivariate normal distribution with mean vector 0 and covariance matrix sigma square in. Now, you understand what is the meaning of multivariate normal distribution, right? And you know that it will be required when we try to conduct the test of hypothesis and confidence interval estimation. There are two more assumptions which are required to study the last sample properties of the estimator that we are going to find. So, one of them is like limit n tending to infinity x transpose x upon n is equal to delta, and this exists and it is a non-stochastic and non-singular matrix, right. Remember one thing, don't get confused with this delta. This is not the Mahalanobis distance, right? If you remember that in the test of hypothesis we had indicated delta square to be the Mahalanobis distance, right? But it is not like this, right? It is only a delta, some matrix which has got the finite elements. And we also assume that that limit tending to n tending to infinity x transpose epsilon upon n is equal to 0. Right. So these two assumptions are going to help us when we try to prove the consistency property of our estimator that we are going to find. Right. Now we come to the aspect of estimation of parameters. The question comes here, why it is needed. Let me try to give you here a very simple example to explain you. You all have studied the equation y equal to mx plus c, which is the equation of a straight line like this, right? And if you try to recall, it is like this actually. This part here is c and this here is the slope parameter, which is indicated by here m. So m is going to indicate the slope of the line and c is going to indicate the intercept term of the line. If I try to divide the components of this equation into two parts, x and y, and another here is m and c. Now I ask you question number one. The question number one is that if you know x and y, then do you have the complete information about the line? For example, if I say x equal to 2 and y equal to 3, then my this equation becomes here 3 is equal to 2m plus c. My question number two is that if I know if I know the value of m and c, if the values of m and c are known, suppose for example I say here m equal to 2 and c is equal to 3, so my equation becomes here y is equal to twice of x plus here 3. Now, in the question number one and question number two, what do you understand? In my opinion, if x and y are known, then we are not getting any more information from this one. No other information about the line. Means I cannot know anything except the information that x takes value 2 and y takes value 3. But on the other hand, if I try to take here the second example, and if I know the value of m and c, then my equation becomes here y equal to 2x plus 3, and then I have here the complete information about the line. What does this mean? That I know what is the slope, what is the intercept m, and for any value of x I can find out the value of y. So, if you try to see here, this m and c, they are playing a very important role in determining this straight line, right? So, I can say that m and c are the parameters of this line. And now you have seen that if somehow you know the value of the parameters, then you know the whole line. Now, my question to you all is that can you extend this concept to the multiple linear regression model? You are trying to write down your model here y equal to say x1 beta 1 plus x2 beta 2 plus up to here xk beta k plus epsilon. Now you want to know this model. So if somehow you know the value of beta 1, beta 2, beta k, and yeah, because obviously epsilon also follows a normal 0 sigma square, so sigma square is also unknown. So in case if you somehow know the values of beta 1, beta 2, beta k and sigma square, do you believe that you have the complete information about the line? The answer is yes. And that is what we mean by the statistical modeling. So in very simple word, I can say that when you say that I want to know this model, this is equivalent to saying that you want to know the values of the parameters of the model. Different models may have different sets of parameters, but somehow if you know the values of those parameters, then the whole model is known to you, and after that you can use it in different applications. So the next question comes here, how to know these parameters? So definitely one most simple option is that you try to collect the data on your variables and then try to find out the value of these parameters. And now you have understood. Some time back I had given you a lecture on estimation of parameters. So we had talked about the maximum likelihood estimation, and but definitely I had told you that there are different types of estimation which are available, and among them, yeah, maximum likelihood estimation is quite popular. So here in this now lecture I am going to use here two methods. One is the principle of least square and another is the method of maximum likelihood estimation to estimate my parameters beta 1, beta 2, beta k and sigma square, right? And when we try to use the principle of least square, then there are different types of methods which are available in the literature based on the principle which is behind the least square. So among them, we are going to use here the ordinary or direct least square estimation, which is based on minimizing the random errors in the vertical direction or the y direction. And secondly, we are going to use here the method of maximum likelihood. Well, I'm not going to give you here that much mathematical detail, but I will give you only the some broad steps, and then I will try to show you how you can find them out. Right. So first I try to consider here the direct least square estimation or the ordinary least square estimation. So let me try to give you this idea in the case of a simple linear regression model where I have only one variable x, and my simple linear regression model is y equal to beta 0 plus beta 1 x plus epsilon. So if you try to see here, when you try to have say small n sets of data on say here xi and here yi, they can be plotted here like this, right? So definitely, ideally, you expect that all the points should be lying exactly on the line, but in practice, it is very difficult because of the involvement of the random error, right? So if you now try to find out here a line in such a way which is passing through with the maximum number of points, and now you can see here there is some error which is happening in each and every observation. For example, if this point, this is observed value, but this point is expected to lie somewhere here on this line, right? So if I try to see here, suppose this is my here xi, yi, which we are observing. So this is suppose here capital Xi and capital Yi, right? So all these points which are lying on this line, they can be modeled by y is equal to beta 0 plus beta 1 x, right? And you can see that this error is due to the random variation and different aspect. Yeah, later on I will try to interpret this error in a different way. I can tell you here the name residual, but later on I will try to explain you what is this. But similarly, if you try to see here, some points are below the line also. So these are also error, and different observations have miss error in either which are in the upward direction from the line or in the downward direction from the line. Right. So what we try to do, we try to take the sum of squares of this random variation, like as this one, etc. And then we try to minimize them. And you have understood earlier when we did the graphic that we had used the command plot in R software so that you can make such a scatter diagram, and you can also find out draw there a line which is passing through with the maximum number of points that we already have done, right? So this is how you can do it. So the direct least square estimation involves the minimizing the sum of squares of difference between the observation and the line in the scatter diagram, right? So if you try to see here that once you try to suppose, I can say here now, if you try to look at here in this picture, suppose I can see here this is my epsilon 1, this is my epsilon 2, this is my epsilon 3, this is my epsilon 4, this is my epsilon 5, because this is the difference between the observed and the values which will be obtained from the model. So if I try to write down here epsilon 1 is square plus epsilon 2 is square up to here epsilon 5 is square, and then this will be equal to simply here yi minus beta 0 minus beta 1 xi whole square, and then I try to minimize this sum of squares, and I try to find out the value of beta 0 and beta 1, right? So this is actually done in the principle of least square. We try to minimize here in this case by using the principle of maxima and minima, that we try to differentiate, partially differentiate this equation with respect to beta 0 and beta 1, put them equal to 0 and find and solve them. And they are going to give us the value of beta 0 and beta 1, which are going to minimize the sum of squares, right? So the same thing is done in the case of multiple linear regression model here like this, y equal to x beta plus epsilon, and we try to minimize summation epsilon I square, which I goes from 1 to n, which can be written here as epsilon transpose n. Epsilon, this is equal to y minus x beta transpose y minus x beta, and we try to minimize this quantity with respect to here beta, substitute equal to 0 vector or null vector, and then we try to solve it. So once you try to solve it, then you get here the value of here beta hat, which is the value of the beta which is based on the observations on x1, x2, xk and y. So this value I am going to indicate by here b, and this is here like this. So the ordinary least square estimator of beta is obtained here like this: x transpose x whole inverse x transpose y. Right, I'm not giving you here the exact proof and details that you can find in all the books on the regression analysis, which is very common. But if you try to see here at the structure of this one, here you are trying to find out x transpose x whole inverse. So in order to do it, to find it out, you need the condition that x transpose x is a non-singular matrix. And for that, the rank of x has to be a full column rank matrix K. That was the reason that I had assumed here this assumption, rank of x equal to K. Right. So this rank of x equal to K is going to ensure that this x transpose x whole inverse into x transpose y can be computed, and this is called the ordinary least square estimator of beta. And if you try to see here, this is a k cross 1 vector. And similarly, if you try to find out the estimator of sigma square, then this is obtained here like this: sigma square hat, which is equal to 1 upon n minus k y minus x b transpose y minus x b. Well, I'm not going to give you here the detail, but still I will just give you here the quick guidelines. I have given you the idea that what I have done. Right. So if you try to see here, I'm trying to consider here the summation epsilon I square, and suppose the value of beta which are going to minimize this sum of a square are indicated by b1, b2, bk. So this sum of square deviation can be written here as a y minus x beta transpose y minus x beta for a given value of y and x. And yeah, means mathematically the minimum will always exist, because this function s beta is a real valued convex and differentiable function. So if you try to see here, I'm just giving you the step here. As beta can be expanded like this, then we try to differentiate as beta with respect to beta, which is here like this. And then if you try to see the second order partial derivative is at least non-negative definite at the value of beta which we are going to get from this equation is really going to minimize the function s beta. So try to obtain here the normal equation by partially differentiating the s beta with beta, then we get here these equations. And from here we try to obtain here b is equal to x transpose x whole inverse x transpose y, which is the ordinary least square estimator of beta. So this is how you can obtain the estimator. Now, yes, and you will see that once you know this value, so this b here is a function of here only x and y are known, and hence this b is known. B is also known to us, right? So now you can see here in the model y equal to x beta plus epsilon, this beta was unknown to you, and now you have obtained the value of beta on the basis of given values of x and y, which are indicated by here b. So beta hat equal to here b, and now since the parameters beta 1, beta 2, beta k are known, sigma square can also be estimated by this function, this estimator. So now I can say that we have obtained the multiple linear regression model. So now I try to give you some smaller definition which are helpful when we are trying to do the regression modeling. And now onwards we are going to simply assume that X is a full column rank matrix unless until I. When X is not the full column rank matrix, then it gives rise to the problem of multi-collinearity. But I am not going to discuss it here. Right. So now you have obtained the value of beta as beta hat is equal to b. Now your model was equal to here x beta plus epsilon. So now your fitted model is obtained just by replacing the value of beta in the model, which is here y equal to xb, right. So this fitted line or the fitted model or fitted linear regression model is obtained by y is equal to b into x. Now if you try to give some particular values of here x, right, then you can obtain the fitted value, right. So if I say here, suppose x is something, then you can obtain here the value of y, and suppose that way I try to denote here, say x into b. So the fitted value of for a given value of x are obtained by here y hat is equal to xb. And now if you try to substitute here the value of say here b, which is x transpose x whole inverse x transpose y, then here we have got a specific matrix, this one, x into x transpose x whole inverse into x transpose. This is indicated by here h, and so this expression becomes here hy, and this matrix H is termed as hat matrix. Yeah, hat matrix has an important role when we try to analyze the statistical properties of different estimators in the multiple linear regression analysis. For example, this hat matrix is symmetric. This is idempotent, that if you try to multiply h and h, the outcome will only be h. And if you try to find out the trace of h, so the trace of h here is, if you try to remember the rule, trace of AB is equal to trace of BA. So we try to use this as here A and this here as here B, and I try to bring this x transpose x on this side. So this becomes a trace of x transpose x into x transpose x whole inverse, which is trace of identity matrix of order k, which is here k. So you will see that when you try to understand the topics in the regression analysis, then you will need these properties. Okay, now I give you one more concept, which is about residuals. What is this? This is essentially the difference between the observed and fitted values of steady variables. And if you try to recall this picture which I had just shown you, earlier I had taken this difference here as say epsilon. But now what I am trying to say, that you try to obtain the value of y from say here by the fitted model, y equal to y hat is equal to suppose xb, and this is here the value which you are trying to observe, say here y. So if you try to see this difference which I have indicated in red color, this looks very similar to what we had interpreted as a random error in the earlier picture. So I'm not saying at all that the random variable can be estimated. Please don't misunderstand or misquote me that I have told that we are going to estimate the random variable, but if you try to see here, both this picture look like same. So what we try to see here, that the difference between the y and the fitted value of y may give us some idea about the random errors, and you will see that many diagnostic tests are based on this concept. So if you try to take this difference and let us consider y minus y hat, so y hat is equal to xb, and we also have seen that y hat is equal to hy. So if you try to see here, this is here I minus h into y. So I try to indicate this I minus h as here h bar, right? And so this E, which is a residual vector, can be indicated by h bar y. Well, all these things, either this is B, fitted value, residual vector, they will be obtained in the R software. So it is important for you to first understand what they are trying to explain you when you look at the software outcome. And then this h bar also has some nice properties. That h bar is symmetric like h. H bar is also an idempotent matrix like as here h, right? And trace of h bar is equal to trace of in minus trace of h. So this is here trace of identity matrix of order n. So this is here n, and trace of h we already have obtained by k. So these statistical properties I am explaining you because they will help you later on when you try to understand the further topics in the regression analysis. Okay, so this was about the ordinary least square estimation. Now I come to maximum likelihood estimation. Right. So when we try to consider here the model y equal to x beta plus epsilon, now we are additionally going to assume that the errors are normally distributed and they are identically and independently distributed. Remember one thing, what is the difference between ordinary least square estimation and maximum likelihood estimation? In the ordinary least square estimation, for estimating beta or sigma square, we don't need any assumption on the distribution of the random error, for example, normal or anything else. But when we are trying to consider the maximum likelihood estimation, then we have to assume some distribution of the random errors, because maximum likelihood estimation depends on the likelihood function, and likelihood function is obtained as a joint probability function of the random variables. So that is why it is important for us to now assume that epsilon is following a multivariate normal distribution with mean vector 0 and covariance matrix sigma square I. Well, this assumption was made as one of the assumption of the multiple linear regression model, but we are going to use it here. And after that, we are going to use when we are trying to conduct the test of hypothesis and confidence interval estimation. In that case, yes, in case if you are trying to use the least square estimator, then you have to make a distinction that, okay, you have obtained the least square estimation without assuming any distribution for the random errors, but when you will be conducting the confidence interval estimation and test of hypothesis, then you will be requiring that assumption. So this is the basic difference which you always have to keep in mind. So we know that the normal density functions form is like this. So the normal PDF of epsilon I is obtained here by 1 upon sigma root 2 pi exponential of minus 1 upon 2 sigma square into epsilon I square, for I goes from 1 to n, and all of them are independent. So I can find out the likelihood function as the product of this individual PDFs, which is obtained here like this, and then summation epsilon I square I can write down here as epsilon transpose epsilon, which is written here as a y minus x beta transpose into y minus x beta. Now if you try to take here the log, and if you try to partially differentiate it with respect to beta vector and scalar sigma square, you get here these two normal equation. If you try to recall, we have done a similar exercise when we had obtained the maximum likelihood estimation in case of a univariate as well as multivariate normal. There we found the likelihood estimators for mean vector mu and covariance matrix sigma in case of multivariate normal distribution, and we had obtained the maximum likelihood estimate of mu and sigma square in case of univariate. But here this sigma is like here sigma square I. So that is why if I try to estimate only sigma square, that will give me the complete estimator of the sigma hat also. Right. So that is why I am trying to differentiate it with sigma square. And if you try to solve them, you will get here the these two estimator. The maximum likelihood estimator of beta is indicated by here beta tilde, which is here x transpose x whole inverse x transpose y, which is same as OLC, ordinary least square estimator, or the estimator that we obtain by direct regression. And but the maximum likelihood estimator of sigma square is indicated by here sigma tilde square. It is here like this 1 upon n into y minus x beta tilde transpose into y minus x beta tilde. But you can see here the difference here is with the divisor. Here the factor is 1 upon n, where the divisor is n, and in the case of direct least square estimator of sigma square, you can see here it was 1 upon n minus k. Right. So that is the basic difference between this ordinary least square estimator and maximum likelihood estimator. And anyway, the ordinary least square estimator of sigma square is an unbiased estimator, whereas the MLU of sigma square is a biased estimator of sigma square. That is the main difference. So OLSE and MLU of beta, they are the same, but OLSE and MLU of sigma square are different. That is what you have to keep in mind. And you can, I am just trying to give you some steps so that you can verify later on that if you try to find out the second order partial derivatives with respect to beta sigma square and beta and sigma square here, and then try to find out the border Hessian matrix, and it will ensure that whatever value you have obtained for beta equal to beta tilde and sigma square equal to sigma square tilde, they are really going to maximize the likelihood function. So how we try to consider some properties of the least square estimator, they are discussed for your information, that OLC of beta is an unbiased estimator of beta, that is expected value of B is equal to beta. If you try to find out the covariance matrix of B, This will come out to be here sigma square into x transpose x whole inverse. And now if you want to know this value, then it is dependent on sigma square, and sigma square here is unknown. So in practice, what you can do, if you want to know its value, then you can estimate sigma square, and an unbiased meter of sigma square is obtained here. This is obtained as sigma hat square is equal to 1 upon n minus k y minus xb transpose into y minus xb, and this is indicated by here s square. And once you have obtained this thing, this value of sigma square can be substituted here, and we find an estimator of the covariance matrix here like this, sigma square hat into x transpose x whole inverse. And you will see that I will try to show you all these things in the outcome of the software. So it is important for me to at least give you here this idea that what are these values and how do they look like. Similarly, if you try to find out the covariance matrix of y hat, that is the fitted vector of value, so this will come out to be here sigma square into x transpose x whole inverse x transpose, which is sigma square h. And once again, here this sigma square is unknown in real data sets, so you try to estimate it by sigma square hat, and you try to replace it here, and so the covariance matrix of y hat, which is the covariance matrix of the fitted values, it is obtained here by replacing sigma square here, and it is coming out here sigma square hat h. And yeah, one question comes here, what about the values of this beta in this model that we have got? So just to convince you, we have here Gauss-Markov theorem, which explains or which mathematically proves that the ordinary least square estimator is the best linear unbiased estimator of beta. Right, it has got the minimum variance in the class of linear and unbiased estimator. Beside this thing, I can also tell you, I'm not going to prove it, that the ordinary least square estimator is a consistent estimator of beta, and this is sigma square hat, which is indicated by s square, is also a consistent estimator of this sigma square. Right. So now we come to an end to this lecture, and you can see here that was a pretty lengthy lecture. But if I try to break it into two parts, then I will have to repeat many things. So my advice is that you have an option that you can watch this video in parts. But if I try to break it, then it will be difficult for me to continue, and it will also be difficult for you to maintain the continuity. So that is why I decided that I should give all these basic concepts in one lecture, because now after that I will be going to different aspects where I am going to use these concepts. And then you will see that when I am trying to conduct this analysis in the R software, then you will have only their numerical values. But there I will try to show you that this is the value which is called as, for example, fitted value or ordinary least square estimator, etc. So now it is your turn, that if you want to clearly understand the lectures which I am going to give now in the forthcoming lectures, if you want to understand the content, it is very important for you that you understand these basic definitions. In case if you cannot remember the expression, no issue, but at least you must know what they are trying to indicate, how they had been obtained. Because in the software, they will simply try to give you some numerical values which are based on the data set of x and y. But what are they going to explain you? This is our job. And I would say that, okay, I have not given here many proofs, many mathematical derivations, but I tried my best to strike a balance so that those participants who have a good background in mathematics and statistics, it should not feel lonely. Right, but definitely for those who are interested only in the application, they may or may not be interested in the mathematical details. But definitely, as I said in the last lecture, that this regression analysis has many more topics which are available in the books and which I am not covering here. But I will try to give you the sufficient background so that if you want to understand those topics, you should not face any problem. But definitely, you have to study, you have to work hard. So you try to revise this concept and come prepared for the next lecture, where I will try to take up some more topics. So you try to practice it, and I will see you in the next lecture. Till then, goodbye.